I'm going to start out with two questions before I start. And the first one is, I mean, in the Feynman lectures, the first chapter already talks about the importance of atoms and how they attract each other when they get close and repel each other when we press them onto each other. And so the one question is that true under all circumstances? That's one question. And another question I want to address here in this talk is that Jim Dziemjewski has called the invention of STM a black swan event. So a black swan event is an event that comes as a surprise, has a major effect, is often inappropriately rationalized after the fact with the benefit of hindsight. So the question I want to look at is, what do we need to do to keep the music playing? I mean, the introduction of STM and AFM was a huge breakthrough, and of course, it's important to wonder, how can we keep this on? And so my talk, the title, Chemical Bonds to Natural and Artificial Atoms Resolved by Subatomically Resolved AFM. And so I want to just introduce myself a little bit. So I had the great privilege to work with Gerd Binnig during my PhD time. And after that, I went to Silicon Valley and developed with Park Scientific Instruments the first AFM that could resolve silicon. And then I quit science and worked in management consulting. And in my home lab, I invented the Q+ sensor because of the challenges I had faced with resolving silicon. Then I was a group leader in Augsburg with Jochen Monhardt, and then got offers for Regensburg and for Bristol. And since 2006, I'm now in Regensburg. So my group, just it's an old picture before Corona, actually. So I want to start out with the second question. What do we need to do to keep the music playing? And it's always a good idea to do a benchmark or to look at other fields, how this has happened. And I had the great pleasure to meet one of the most important living painters about 20 years ago, Gerhard Richter, because he had seen a picture in a newspaper of an atom, and he created a piece of art out of this. And he was also interested in how this works. And when we first met this 20 years ago, he also gave me his biography. And I was really curious because his challenge was that he was born in 1932. And when he studied art, painting was dead. So he actually left the German Democratic Republic in 1961 and fled to West Germany and started over studying art again. And today, the greatest museums worldwide, they proudly display his works, and his exhibitions still draw huge crowds, and collectors pay up to $40 million for his paintings. So painting is not dead. Now, sometimes people say, oh, scanning probe is dead. So that's why I think that's a very relevant question. And that's why for me, it was very interesting to meet this man and to exchange ideas. And I just finished writing up a little book about our encounter. So this is one piece which is actually in San Francisco. I think currently it's de-installed, but in principle it's in the Young Museum. And just 2 months ago, I finished writing this book about our meetings and about the exchanges of ideas. So if you look at famous scientists, you can always ask, what do they do to train the right side of the brain? So for instance, Gerd Binnig, he plays the guitar, he was painting, sculpting. Gerhard Ertl, he plays the piano. George Bednarz does sculpting. Roald Hoffmann does poetry. And Richard Feynman played the bongos, and he also was a pretty bad womanizer, which I think he also used his right half of brain for. So I'm going to now go to the real scientific question. So attraction and repulsion, is that true under all circumstances? So this is the schematic dependence of these inner atomic forces. We first have attraction, and then we have an equilibrium distance, and then repulsion again. So Heinl Rohrer actually defined the successful demonstration of vacuum tunneling as the birth of the STM. So you can see here the slides of the exponential decay of tunneling current. And that's a very important property of the current, and that makes the STM relatively simple compared to the AFM. In the AFM, we have an extra challenge that in principle, we want to measure the front atom's force to the sample atom next to it. And we have the challenge that this force is concealed behind much stronger van der Waals forces. And then it's not monotonic, initially attractive, then repulsive. And then it's hard to measure because it's very difficult to measure small forces with a good signal to noise ratio. So the method which was proved to be successful was frequency modulation AFM, where you are oscillating a cantilever close to the sample, and then you measure the frequency shift, and that allows you a very precise measurement of an average force gradient, of an average tip sample force gradient. And now it turns out that using that technique, you can actually resolve silicon 7x7. That was a big challenge. Even Binnick thought at one time it was impossible, but it actually was possible. So the technique used here was frequency modulation with soft cantilevers and large amplitudes. But these large amplitudes have drawbacks. If you do the math, you find out that using a large amplitude is required for stability. Otherwise, you would suffer a jump to contact. So if you take this relatively soft cantilever and you vibrate it only by an angstrom or so, you bring it close enough to sense the atomic forces, that it will just jump to the surface. It will form a chemical bond, and the tip will be destroyed. So the solution was to come up with a much stiffer cantilever. And that was actually triggered by my work as a management consultant, because we did a lot of benchmarking studies with our clients. And at that time I thought, okay, so who is best in measuring time and frequency? And that's the clock makers, basically. And this clock revolution, the quartz clock revolution, really was important in the fields of timekeeping. And by accident, if you calculate the stiffness of this prongs here, so this is the timekeeping element of a watch, of a quartz watch. It's a metal cylinder. If you take it out and open it, you find a quartz tuning fork inside. And if you lock down one of the prongs and put a tip on the other one, you have an AFM sensor, and it's close to ideal. Already this watch type is almost perfect for getting stable oscillation at angstrom amplitudes. So the question here was, can you vibrate this at angstrom amplitudes? Because in the watch, it vibrates at amplitudes of about 10 micrometers. And it turned out positive. It is possible. So that's why a replacement of the silicon level with that proved successful pretty soon. So already 2 years later, we first got atomic resolution on silicon, and even what we called subatomic resolution, although in the tip, because the sample here, the silicon 7x7, exposes single dangling bonds, and the split image here is caused by the structure of the front atom of the tip. So the tip is a great challenge. I mean, Leo has already shown this to us. So one question is, how can you probe the tip? Can you find a way to really learn as much as possible about your tip? And this is a method which we have called COFI, carbon monoxide front atom identification, where we use a CO, it's often a copper or another metal, and then it probes our tip. And the nice part is we can do STM and AFM at the same time. So here we are now looking at a video on the left-hand side, you see the tunneling current. On the right-hand side, you see a frequency shift. And in this video, every frame is recorded at 10 picometer less distance than the one before. So we start out at a reference distance of 380 picometers, and then we go frame by frame closer and we watch what happens. So first we see on the current over the CO molecule, we see a dip. We see approximately 1/3 of the current less in the center than outside. And in the frequency shift, we see now a contrast of about 0.3 hertz. We see attraction over the CO molecule. And now as we start, signal to noise gets better, but something even more interesting happens. If we look at the sizes, we clearly see that the image of the current is much more blurry than the image of the frequency shift or average force gradient. And so we see a tiny spot in the AFM signal and a much larger one in the STM signal. And we can even see these 4 bright bumps in the back here. Those are caused by the second tip layer. So we can already see some influence of the second tip layer here. So that's a nice way to learn about our tips. So STM and AFM thus map different electronic states. Now, if we look at silicon again, so this was the first result on silicon 7x7 atomically resolved. That was at room temperature. And this one is one at low temperature, again with a silicon cantilever. This one was at room temperature in our lab, recorded with a Q+ sensor. And this last one here is using a CO terminated tip at 4 Kelvin, again with a Q+ sensor, small amplitudes. And here you can see that the atoms appear to be much smaller, much less diameter, the silicon surface atoms. And you can nicely see the rest atoms of the surface here. Those are about 1 angstrom lower than the surface, the so-called adatoms, and you can still make out a local maximum here. Now, what is the interpretation of this CO tip? So when the CO tip interacts with organic molecules or with silicon for that matter, it's quite correct to say that we have Pauli repulsion, which is proportional to the total charge density. So in other words, the CO tip, first we have some small van der Waals attraction, and then once we get close enough, we get Pauli repulsion. So here we have a small shallow attraction going into a repulsion. And of course, the question is important whether that's this way all the time. There was a little surprise when looking at metal clusters. So here we look at 3 metal clusters, a dimer, a trimer, and a tetramer. And the STM signal is very similar for all 3, except for the height, I mean the brightness, but the full width at half maximum is actually fairly similar. But in the AFM, you can really count the atoms. But surprisingly here, you don't see a bump in the center of the atom. I mean, this is a dimer, so there's an iron atom here and an iron atom here, and yet it appears like a torus. And here the trimer appears like a sum of 3 tori, and the tetramer like a sum of 4 tori. So that's a bit surprising. And also the substrate. So here on this figure with the larger clusters, you can see the substrate, and the surface atoms of copper appear attractive here. So here it seems that maybe this notion that the CO tip interacts repulsively via Pauli repulsion is not true in all cases. That's a very interesting point of fundamental importance, of course. So we now managed to use CO tips also for atomic manipulation. So you see here are 5 iron atoms. And Julian Beerwanger, the first author of this paper, he pushed those atoms together and formed clusters, dimers, trimers, tetramer, pentamer. And then again, they are not showing a maximum where the total charge density is maximum. So that's a very interesting question why that is. In the 3D version, you see it a little better. Here again, that's the van der Waals attractive ring. That's very similar to the organic molecule data, which Leo has shown us. But what's interesting is, why do the atoms not appear in the right contrast, right in parentheses, of course? So that's a question I want to look at in the second part of the talk. So here, lots of people now use the Q-plug sensor. So in this review article, there are many contributions from colleagues around the world. And it's very important to have all kinds of experiments. And in very many cases, this repulsion of CO tips holds true, but not in all cases. And that's quite an important question to ask. So here, we looked very closely at a single iron atom. So it not just shows a torus, it even shows 3 bumps on the torus. So that's the AFM image of this single iron atom on a copper surface. And the question is, how does that come about? What is the origin of this contrast? Our first attempt to explain this was this. Okay, we thought both iron and copper, they have a full or almost full 3D shell. And then they have a 4s electron or 2 4s electrons for the free atom, like iron. And we thought, okay, if this atom would hybridize with a pZ state, it could push more charge into the volume, into the bulk of the copper underneath. So basically, this is a z-axis here. And for negative z, that means inside the copper. So if you look from the top, you would see a ring. So this would be compatible with the CO interacting via Pauli repulsion with total charge density, because here the total charge density indeed would show a ring. However, this interpretation was wrong, because if you do the DFT calculation, if you put a iron adatom on a surface, it actually turns out the charge density, the total charge density, is more or less Gaussian. It's not ring-like. So we compared 3 different adatoms of copper: silicon, copper, and iron. So here we look at silicon. We have the normal behavior, which we already know from bulk silicon, from silicon 7x7. So as we approach the tip from the z direction, we first see a van der Waals attraction. It's rather weak, only about minus 20 piconewtons. And once we get closer, we see Pauli repulsion. And the atom appears like it should, like a small dot which interacts repulsively with our tip. Now with the copper adatom, it's different. Again, we see the van der Waals attraction over the center of the atom, but then it turns repulsive as we get closer. But if we go a little bit outside in a circular arrangement, the repulsion comes much earlier, and the van der Waals attraction is much, much weaker. So we see this repulsive ring around here. And for the iron adatom, it's even more interesting. Again, if we approach in the center, we first see van der Waals attraction, then we see repulsion, and then we see a strong repulsion inside. Attraction inside again. And the repulsion is also stronger on this ring geometry. If we look at this from the top, this is again the silicon on the left. The copper, the contrast here is such that the scales here are similar to the left one, but of course the contrast is pretty strong. It's very easy to see this in the experiment. And for the iron, we see also a ring with 3 bumps on it. Now our colleagues Svetlana Polesia and Sergei Markovsky and Hubert Ebert did the DFT calculations here, and they actually confirmed this. So in the DFT calculation, if you let a CO tip, actually they only used a CO molecule, a naked CO molecule. If they interact, let this interact with a silicon surface atom, they find this contrast. With the copper, they find this, and with the iron, they find that. If you look very closely, you see also in the copper, they would find a very small modulation here. There's maybe about 1/3 of the contrast here, but experimentally, we could not see this so far. But it's nice that DFT confirmed this, basically the contrast of the single atoms. And what this basically refers to on the iron is that we see an experimental version of the transition from physisorption to chemisorption. Some adsorbates, they can bond in 2 ways on a surface. They can have a stable physisorption state if there is a barrier, and then if you push through the barrier by enough thermal energy, for instance, you can form a chemisorption state. And basically, the AFM allows us to do this in a controlled fashion here. So again, this 2D versus 3D image here. So we see this ring-like structure on the top view with the 3 bumps, and we see the force profile in the center if we cut a line through here. Now the DFT shows how these 3 bumps, are related to the substrate underneath, because the iron atom sits on a hollow side of the copper, and the maxima of the bumps are actually, they lock to the substrate, of course, because the substrate breaks the rotational symmetry of the iron atom. And so the maxima, you can see, are at phi equaling 30 degrees. That's this point here. So the maxima are over the hollow sides here. And over this hollow side, we have a maximum. And over this hollow side, we have a maximum. And so that's also nice that not just the fact of 3 bumps is revealed, but also the angular orientation. Now, if the CO tip is tilted, then the contrast is weaker, and it's also the height of these 3 bumps is different. So you can show that in the calculation that this, of course, affects the symmetry, not too surprisingly. And another interesting fact is for copper adatoms, because there, as you approach, you first have van der Waals attraction, then you start to see the ring-like repulsion. The repulsion becomes stronger, so the line becomes sharper. Interestingly, that's a very similar behavior as in a carbon ring in an organic molecule in the pentacene data, which Leo has shown us. But then inside the copper, you see a strong repulsion again. And that is also confirmed by DFT, by these lines. So you do see this contrast. A maxima is coming up inside if you get even closer here. Okay, so that concludes my discussion of single atoms. And now I'm switching over to artificial atoms. So in 1993,
Franz, just to FYI, we only have 5 minutes left for the whole meeting.
Yeah.
So if we could leave room for questions, that would be awesome. So do you think you could sort of either quickly get through the artificial atoms, or perhaps we leave that for another day?
I think I can do it very quickly. So, okay. This is a famous corral, and it encloses 102 electrons. And the question is now, how do these electrons bond to an AFM tip? And this is a question we answered here in this paper. And well, I'm not going to go through the math here, but essentially there are two types of electrons, the one at the Fermi level, that's the ones we see by STM, and the total charge densities, which we are sensitive to in AFM. And so STM and AFM do provide different, let me just go to the final, to this one here, do provide different contrasts. So the STM channel shows us the electronic states at the Fermi level, and the AFM contrast shows us the total charge density inside, and that's what we can confirm here. So, okay, and then we also affect the occupation of states. So the tip sample interaction alters the states. That's another nice thing we can see, we can study by the AFM. And another nice thing, with these large artificial atoms, we can easily disturb the atom inside by putting an extra atom there. And then we change the Hamiltonian inside, and we can get very interesting patterns inside in the corral. Okay, with that, I'd like to sum up. So AFM is cool. Stay tuned and watch what's happening. Thanks so much for your attention.
Amazing. Thank you both. We have 4 minutes for questions. So I want to just really open it up to anybody who has a quick question. Go ahead and raise your hand. I think it's probably the most orderly way of doing that. Or use the raise hand button.
Could also answer very quickly the questions in the chat.
Yeah, that'd be wonderful.
Okay, there were 3. One was if we can use that to solve Schrödinger equation in a neural network. So I had half an hour to think about the question now. I still don't quite get it. So the benefit would be to use single electrons, but it's very far away for that application.
I guess so. To clarify, there are people who are working on like things like I think it's like FermiNet, like basically using neural networks to do much better simulations at the atomic scale. And the thought would be like, could you in some world like create like a closed loop system where the network learns to predict what's going to happen, and then like does the experiment with the tip, and yeah.
I think from a generic point of view, that's possible. We are thinking about that, but it's very far from realization because of the problems to connect single molecules with multi-terminals mainly, and other problems. So principle, okay. Yes,
thank you.
But very tough. And there was a second question that I liked a lot, and that was whether we can do an anti-aromatic carbon ring. So the one we made had 18 carbon atoms, and that's not only aromatic, it's even doubly aromatic. So it has 2 18 electron systems, and that's the carbon ring that's was proposed to be the most stable one. That's why we aimed for it. So an anti-aromatic one would have 2 anti-aromatics pi systems. So like C20, for example, 4n multiple electrons. And this will be less stable, but it would be very interesting. And we are completely on it with the same team. And let's hope we get to see how that works. That's and the final question was also nice. But now I forgot it. The molecular machine, if you can drive that with single electrons. Absolutely. No? So a single electron can do a huge conformational change on the molecule. And so it's plenty of energy. It's like you have 1 eV or 2 from one electron, and that will be enough energy to drive an electron. At room temperature, you might need a little bit more, and of course, then you compete with thermal energy, but also not that far off, I would say. Certainly at low temperature.
Awesome. Unless anybody has one more really quick question. Allison.
In the 1 minute that we have left, I usually always try to sneak in the question of what's the #1 undervalued challenge in your field right now? If I was new coming to the field, I want to get my hands dirty. Is there one thing that you want to point people to?
Yeah. I mean, I have one which I already sent you by email, and that's, I mean, when Leo and Gerhard Meyer, when they found that this CO tip is so effective to improve resolution, we would love to have such a tip which works at ambient conditions. I mean, first at room temperature in vacuum, but then in ambient conditions, that would be fantastic. Because all the wonderful stuff Leo showed us about organic molecules, imagine if that was possible on your desktop bench. I mean, that would be absolutely amazing. I don't know, Leo, what do you think about that?
Yeah, I mean, there's several things. That's one that would be super to look 3D, to get these images in 3D. That would be also great. So far, we are limited to the surface. No? Another thing that's actually where there is a lot of progress and that would offer unique progress is to increase time resolution in these atomics manipulation images by combining it with laser experiments from probe. Yeah, so I think there's a lot of nice things coming up.
Thank you so much to both of you. It was really wonderful to check in on the results. Very, very happy.
Okay. Thank you, Alison. And
Thanks.
yeah.